Our guest today is Pierre Baqué, the CEO and founder of Neural Concept. Neural Concept uses deep learning to provide industrial companies with lightning-fast numerical simulations and radically innovative designs. Where traditional physical solvers would take days or weeks to evaluate a single design, their neural network-based predictive models allow engineers to test and optimize design ideas in real time. In this episode, we talk about the evolution of simulation techniques in industrial design and how the design cycle can be completely transformed with AI-powered simulations and design generation. We also talk about the future of human-machine collaboration in design and how to break world records in speed. Pierre, welcome to the show.
Thank you, Artem. Very happy to be here.
You're enabling industrial companies to radically change their approach to design with AI-powered simulation. Let's start with a brief history of the simulation techniques. How did they evolve over time, and what new capabilities are enabled by deep learning?
So, I think it's interesting to note that the history of simulation is as old as the history of computers themselves. So really the first computers were used primarily to solve differential equations in the context of flight ballistics and so on. So it's pretty old history. Then around the 70s, so this is like really with the early computers. Then around the 70s, 80s, simulation codes, a bit in a more modern way, as we know them, started to emerge in order to attempt to replace testing in industrial companies. At the same time was the emergence of computer-assisted design, so going away from pen and paper drawing to more 3D. At the beginning 2D, digital drawing, and then later 3D. And then really, like since the 80s, 90s, the adoption of simulation, first as a replacement to testing, and then as a way to iterate and try to improve designs, has been more widespread in the industry. And so, of course, the automotive industry was probably one of the first adopters, with as well the aerospace industry. And now it's very interesting to see that this is going really in also many other industries, so including packaging, of course, electronic design, but also the medical industry for personalized medicine and so on. So what does deep learning have to do inside this landscape? So as I was saying, really the core, the essence of the simulation tools was really to replace testing, so make accurate simulations, to not have to test devices in a physical way. But it means that the solvers have always developed capabilities to be quite accurate, but the speed of usage has always remained very limited in terms of so traditional simulation in most domains takes from several tens of minutes to hours or days, and therefore it's very difficult for either for a human engineer or for another algorithm to iterate with a simulation algorithm to try to improve designs and like test many different options. And that, I think that's really where the modern deep learning technologies have a role to play, which is as a surrogate to traditional simulation to accelerate them and be kind of an intermediate between a full-fledged simulation, which will always be a bit slow to run, and another intelligence, which will be either human or another algorithm trying to interact with the simulation, and really putting in between something that can learn from the simulation data but be very fast to answer is where deep learning is playing a role today.
And this is the core idea behind the NC Shape, your product, accelerating simulations and making it available to CAD designers and speeding up the design cycles because of that. So talk about its capabilities and how it changes the design workflow.
So yeah, exactly. As you're saying, it's definitely exactly the core topic of what Neural Concept Shape is doing and offering as capabilities. So the goal of the platform is to, the envision and what we're really trying to develop is to have a central intelligence system that can learn from the simulation data as a very, very useful source of input from all the simulation that can be run inside the company. but that can also be interrogated and used to take very fast design decisions and optimal decisions by design engineers, or as well by other algorithms. When I say other algorithms, to be an algorithm that will iterate with this one. And the typical example that we can see of how NC shape is used is, I mean, if we, and this is, for instance, how this aerodynamic bicycle that broke the world record that we developed has been developed, but also how people in the automotive industry use our tool. It's really, instead of having a design engineer who is sitting on one side and a simulation expert who is sitting on the other side, and having exchange loops that are done, even in the worst case, sometimes manually or through an automated file exchange, that where the designer has to ask for a simulation to the simulation engineer who runs the simulation and sends back the result. So this is really the traditional way of working, to putting in the middle artificial intelligence system, so learning system that can interact on the one hand with the simulation engineer who will train the model, feed the data to make it accurate and able to give fast prediction. Two, on the other side, the designer who will interact with this algorithm, to this predictive model, to get very fast and accurate answers in its day-to-day job. So it's a bit, again, the same thing that I was illustrating before in the introduction.
Right. A traditional way of doing things is design engineer would design the shape of the product in a CAD software and use their experience, use their heuristics that they have to make it optimal, then send it to the simulation engineer, and then wait for sometimes hours, sometimes days to get the results back to see where the changes need to be made, work again on the changes, and send it back to the simulation, run it again. And these are the slow cycles of the traditional way. And then with the NC shape, we can set up the simulation and give it to the designer, to the CAD designer themselves. And now the designer can build this design, test it with NC shape, run multiple tests, and only then send it to the traditional simulation.
Yes, yeah, exactly. Yeah, that's correct. And of course, let's say the designer can be also an automated designer, which is another algorithm trying to interrogate this model to search the space of design. And that's what we call, of course, optimization or AI-driven optimization.
You talk about that, and I read it in your documentation when you talk about 100,000 designs explored in a day with your simulation. So those 100,000 designs are created by that automated system that creates design variations. Is it a part of NC Shape or is it a separate thing?
No, so it's a part, and I think that's what also makes our platform quite unique. It's that we have really worked to integrate all these components side by side, so that they can talk in a very efficient and optimal manner, and work really in conjunction. So in NC Shape, there is also, of course, a part with the surrogate models that we were talking about, the part with the modules that we call design modules that are generating new designs, new design candidates. So this can be done in multiple ways, either through parametric CAD, through morphing functions, through also generative models, which are other neural network algorithms that are able to automatically generate design candidates. And then the optimization loops that connects the two and explores this design space in an efficient fashion. And everything is integrated and optimized within the same platform.
What would be a good example of using design variations in the real world at NC Shape? What kind of results have been achieved with it?
We have very concrete and powerful example of fully automated design in different domains. So some on the really more sports environment, and some on a real industrial environment. So maybe if I can start with the sports side, so two big examples. So one is this aerodynamic bicycle that was developed and broke 2 world records using our software. And now a new boat that is really a futuristic boat that will also hopefully break the speed sailing world record, and that is optimizing its like really completely new way of designing hyperventilating hydrofoil, and retrying finding very original solution using this completely integrated optimization. So that's really more on the sports side. On the industrial side, we have also a lot of applications. So I can cite some electronic components that were completely designed. So at the level of design placement of the electronic parts, using our software, achieving better performance than traditional methods. On the side of heat exchangers as well, which are now some essential components for electric vehicles and the performance of electric vehicles. And some automotive OEMs have been able to completely disrupt and improve by a quite large margin the performance of these heat exchangers using this type of AI-driven optimization. Also on the side of power generation, on different applications, but some turbines that were developed using our optimization techniques regarding multiple type of physics and so on. And I mean, of course, in the aerospace domain with the external aerodynamics of aircraft, we had some drones as well that were developed with our this optimization loop. So, and in every case, we found that the optimization was faster in terms of time that it takes to develop the whole project, in terms of number of actual simulations that you need to do, because you still need to do some actual simulations, but lowering the number of actual simulations, and very importantly in terms of final performance, getting to a level of performance that was not reachable before, and sometimes even unlocking the potential of new concepts that we need to like go above some performance threshold to be viable, and making this possible.
So using AI for design iterations is actually widespread with your customers. And is it fair to say that most of the installations of NC Shape include both simulation and design variation?
I would say 50%. That's 50%. So 50% of our customers are using, let's say, manual design exploration, and the other 50% are using automated design exploration using optimization.
Gotcha. What do you think differentiate these two groups of customers? What are the important steps or important changes that should happen to the other, so the other group that currently don't use the variation techniques can also start using it?
I mean, I don't think it has to be a goal in itself to use optimization. So some customers that are using manual optimization are also achieving very good results, and just by the fact that they can get very, very quick feedback, it changes the way they design and the way they understand their own product. So it's not let's say a goal or a necessity. What differentiates the situations where you can or where you cannot use this is, I mean, it's quite often in terms of how can you express to the machine or give to the machines all the unspoken constraints that the designer is able to take into account when designing manually, but that are very difficult or that is not able to tell a priori to a computer. So that's, I think, what makes the difference. Let's say the hope in that we are really betting on, and that I think is going to happen more and more in the future, is that this constraint and these implicit constraints can also be learned through data by these generative models who are able to learn some design spaces that learn the constraints, and are therefore able to go one step further in the automation of optimization. But I think design, manual design is very, very fair. And maybe one last thing in that direction is, I don't see that, again, end-to-end optimization is completely a necessity. Sometimes the algorithms can also be used to guide the design engineer in the right direction, giving some sensitivities, making some design changes that maybe will violate a constraint, but will give an understanding of what should be the direction where the designer should go. And by having this kind of really hybridized approach to design, where the machine and the engineer can complement each other, is, I think, really a very interesting intermediate between completely manual design and fully automated one.
It is definitely a very powerful intermediate step for the designers to be guided or to have new intuitions inspired by what the simulation done in automatic way. And you also talk about performance increases over design cycles. Curious, why does it happen?
So I mean, at every design cycle, the engineer or the system will generate new actual simulations that are like the data that fuel this surrogate so that it can be accurate. And as the surrogate model sees more and more data from different programs, different concepts, and so on, it gets smarter and smarter. And therefore, for a new program, it will be able to use the knowledge that is accumulated from all the different design iterations and cycles to be able to they get up to speed very quickly. So that's maybe with a really minimal amount of new simulations needed.
Let's talk about the implementation process. So, what are the stages? How long does it take overall?
So usually with customers, and that's not let's say necessity, but it's more kind of a proof of concept phase where we are, let's say, checking on a specific application, on a specific program that this surrogate can indeed be accurate and give a good prediction. And afterwards, we are moving to the implementation phase, which so this proof of concept can be very fast. It can be, let's say, maybe 1 week of work, which will take in total 1 month for the whole project. And then we move to the implementation phase, and this implementation phase is really where we deploy the whole system in the infrastructure of the customer and make this connection between the production data, the optimization. If there is an optimization loop to set up that we set it up and that we connect everything. Again, using the NCS platform, it's since most of the algorithm, I mean, all the algorithms are already here. The infrastructure is almost already predefined. It can be pretty quick. So let's say 2 months of work. 2 months of collaboration. In the best case, maybe can be a bit longer in some cases. But really, with the goal at the end to have a fully integrated optimization loop that where the AI system can let's say have a dialogue with the simulation data, the simulation software, and with the design software inside the company.
So, we're talking 2 months, maybe a little bit more, to get to the production utilization of NC Shape at the organization.
Yes, I mean that's of course there are some delays can always appear, but that's what we aim for in general.
How do you define or measure the success of the NCS implementation at your customers?
Yeah, so that's a good question, and that's really what we are really obsessed with is to be able to measure this success for the customer, and really what we want to measure is the value that the platform and the product brings to the customer, really in terms of our numbers, and we have four axes of values that are possible. So the first one will be to reduce the time that it takes for a critical operation in the critical path for designing a product. So we have some criteria to say that we bring in those value for the customer, but it's really measured in terms of time. Second one will be in terms of cost that is taken. So and it's more in terms of human cost. So the first one was in terms of time and of clock time. The second one is in terms of human work time. The third one is obviously the product quality. So can we measure at the end of the process when using the software? Can we measure an increase in product quality that of course will result in increased either lower cost or increased sales numbers or having some better performance and competition. And the last one would be a reduction in terms of CPU hours cost, or in terms of license cost for other software. So this last one also depends on the cases, but that's also a possible value.
So 4 axes, and you strive to improve time, cost, and quality for your customers at the same time, which is usually, they say, it's a triangle. You cannot achieve all of them. You need to choose two and
Yeah.
sacrifice the third one. But in your case, you're able to achieve all three.
No, I mean, so yes and no. So it doesn't mean that let's say it's options that we can have. Of course, when we measure an improvement, it assumes that the other KPIs remain the same, at least, right? But it let's say to validate the success with the customer, we want at least one of these KPIs to be increased and the other ones to be at least improved, which means moving forward on the Pareto front of options, let's say.
What are some of your favorite case studies with those metrics significantly improved for your customers?
I mentioned different applications. So, I mean, obviously the aspect of improving product performance or being able to unlock some design possibilities using our software is pretty exciting. So, as I was mentioning in the case of heat exchangers, we have been able to improve substantially the performance, and like really meaning like it's very very exciting to see that there is a system that has clearly been designed by an AI system and that is better than what a human could do. That's, I think, very exciting, and in the domain of sports as well, it's also something essential. But the value as well for our customers in terms of speed is very critical, because if you look at the automotive industry, especially for suppliers, there is this concept of request for quotation, and which is I have my customer, which is a OEM that comes to ask for a quotation for a new part. If I can come back to him in 3 days with confidence that I will manufacture this part, it will have this performance, it will cost that much, versus competitor who can do the same thing but it takes 1 month to do. Of course, in terms of business value, it can be absolutely critical. So that's it's something that also happens with our customers in the automotive suppliers with different types of parts. As I was saying, ranging from heat exchangers, ventilation system, also some mechanical structural parts as well.
That makes them able to be more precise in their responses to the RFQ, right?
Yeah, exactly. So more precise and faster and more confident, which means more precise means probably cheaper, and more because they need to take less margin, and faster means maybe that they will win the contract that the competition will not even have answered yet.
They will definitely raise the bar for the rest of the industry, because now the OEM will request or will expect to receive the responses much faster.
Exactly.
What are the limitations of NC Shape? What use cases are not a good fit?
Yeah, I mean, there are multiple potential limitations. So, of course, the data aspect is important. So, the customers we work with usually are, let's say, advanced consumers of simulation, which means it's companies who already have a good established simulation process and who want to improve it. So at this stage, we typically don't work with a smaller company who run maybe 3 simulations per year or 10 simulations per year for a specific application. We like to work with applications or with companies that have a vast amount of simulation. So that can be seen as a limitation in terms of usability. And then the limitation in terms of optimization as well is that what I was mentioning, being able to take into account different constraints from very, very, very complex constraints that are a bit unspoken and that are not very explicit from the designer and from on the design side. But I think that there are really possibilities, as I was saying, with the generative models, and so there are possibilities to improve that. And it's a limitation, but that's actually an opportunity, because it's not only a limitation for us; it's a general limitation of the field.
If anything we've learned over the years is that we find ways to communicate with machines better and better and make them understand our needs more and more. So I 100% agree with you that this is a direction that we can be confident will make more customers able to leverage the generation of designs as well. Let's talk a bit about your AI models that power NCS capabilities. What do you use for that, and how it evolved over the last 4 years that you've been building the company?
Yeah, so we were, me and my colleagues, we were really here at the early days of 3D deep learning. So the disciplines of using geometric convolutional neural network to process 3D geometric data and develop, I think, some of the first performing and scalable algorithms in this domain. And really, we have had a really constant strive to improve the performance of these algorithms, both in terms of accuracy, in terms of data efficiency, which means using small amount of data, in terms of size of the data and stuff, and so on. So that's an effort that is constant and that now has been taken over by our research team for a while. And obviously, another very core aspect of our research and the research that we have pushed, especially with academic collaborations now, is what I was mentioning about the generative models. So having these algorithms, neural networks that are able to generate new geometries out of nowhere, and that's really a second aspect of our research effort at the moment. And then, of course, obviously, putting this together using improving the optimization techniques. And especially, there are lots of optimization techniques that have been developed in the past in the context of traditional machine learning surrogates, and that now have to be revamped and reinvented in the context of deep learning.
What were some of the important challenges the team had to overcome to build your AI system?
First, being able to ingest 3D data at a scalable way and in an efficient and powerful manner is one of the core challenges that we have been working on and still one. And then, always being creative, finding new solutions to every problem, understanding. So we really have a team that is that knows deeply the field of let's say, modern machine learning, AI, computer vision, and so on, and really coming from there, and really trying to fit this kind of impressive and incredible toolbox to the needs of the engineering domain is really constant iteration and thought process. And that's I think what's difficult, but what is as well very, very exciting. And I still think that we are only at and I'm really serious about that. I think we are still at 20% of what is doable in this domain.
Only at 20%, you say. So what are some of the future improvements in the capabilities of the system that you guys working on that you're personally excited about?
At a high level, it's being able to generate this to do that, this first do this optimization with less and less data, really having some algorithms that are purposefully built for some specific physics, specific application, and that therefore less and less data hungry. That on one hand, and on the other hand, being able to generate all these geometries, taking into account more constraints, being more integrated and really smarter with respect to CAD, to the management of CAD data and the generation of CAD geometries, CAD parts, and so on, and really bringing more and more of the AI inside the CAD system is what we want to do.
And for the AI system, the ground truth data that you currently use, this is the CAE simulation data.
So it can be either CAE simulation for the surrogate modeling, or it can be CAD data for the generative models.
Right. Yeah, I was talking about the simulation. So we didn't talk about it. Maybe it's a good time to mention that there are two parts of NC Shape. And the one part is the part where you train the model, and the other one where you actually use its power in the design cycles. So can you talk about what goes into training?
Yeah, so I think it's thank you for explaining that. I think it's quite important to understand that our product is really structured in a way that it's also a data science platform that is that can be used and should be used by the most advanced experts in data science and in engineering data science in the world, who should also be able to benefit from our product. One thing that I want to say that I think it's quite striking for me, there is really this belief sometimes that because machine learning algorithms and the machine learning community is pushing a lot of open source systems these days, open source algorithms, there is really this belief that if you're in a company, in a big company, you can build a small team of smart machine learning engineers and they will be able to let's say bring actual benefits to the business unit by taking these algorithms and making them used by packaging them and making them used by the business unit. And I think that it's I think that's what some companies believed, and now they are coming back a little bit from that, but it's still a belief that is quite present. And I really think that's something that made a lot of people lose a lot of time, because doing proper AI, proper machine learning, and especially in the context of deep learning, is much more than running just a few open source algorithms. It requires a lot of data pre-processing, serious data pre-processing systems, serious data checking, having the right algorithms that are tuned in the right way and implemented in the right way to make them scalable and so on. All the post-processing systems and the right infrastructure to deploy them as well to production. And even with very, very good engineers who start from scratch with Jupyter Notebook and Python and GitHub, we have seen this multiple times that this goes nowhere, and it usually goes to projects that can be aborted. Whereas what we are trying to provide is really a platform so that these engineers can really focus on what they have to add and what they really focusing on the specificities of their problem and specificities of their company, but making sure that they work in the right environment and work efficiently and go to the core of the solution right away without losing all the time that you lose with when you build things from scratch.
Let's talk about the origins of the company. Where did the idea come from, and what became the trigger to start the company?
So I started my PhD around 2013 at EPFL in Lausanne in a computer vision laboratory, and it was a very good moment to be in computer vision, because it's really the place and the community where the new revolution of AI and deep learning restarted in around 2012 with the algorithm that were destroying all the benchmark in image recognition and so on. And there are lots of excitement and ideas very early on that were flourishing in this community about deep learning. We started using really this thing with Theano, like TensorFlow didn't exist, and at the time there was no PyTorch and so on. And then of course moving to TensorFlow. And then around 2015 there was really this first papers about deep learning on graphs, so using graph convolutions to process graphs. So it could be generic graphs, but then also graphs that were representing meshes, 3D meshes. And then more specifically geometric deep learning that really started from graph neural networks. And actually, I remember I went to CVPR, I don't know which year, but there was really this first super cool paper about 3D deep learning. We also were looking at graph neural network ourselves. And that was very exciting. And then I went actually on holiday with a friend who was a simulation engineer, and I also knew a bit about simulation, and we discussed about all this and said, okay, yeah, what if we could use this 3D deep learning on simulation data to emulate this simulation data. And then I started some tests on my laptop using the beginning Xfoil, and then OpenFOAM, and then some student Fluent licenses and so on, and really saw that, okay, even if it was a small scale stuff, that it was kind of working, and it was, at the beginning it was very difficult to make things converge, make things also the limitation in terms of size were very difficult because we were not implementing things right, but really saw the potential. And then started working more and more in that direction during my PhD, and at the end of I also had had a friend who was very excited with me on this work. We managed to have some technology transfer grants from EPFL to transfer this technology into a company. We also had some interest from companies at the time, like from Airbus, PSA, and so on, who were already interested in collaborating. And that's how we started working inside the lab on developing a more professional level code. That was with my friend Timur. Actually, he didn't at the end. He didn't really want to go in the entrepreneurship direction, so he went to work in the US for Facebook, and I decided to continue in this direction. And that's how the neural concept was born. And then we had also, I was very lucky to quite early on meet some extremely talented people who wanted to join the adventure, and also now composing the management team of the company. And that's how it started, and then getting more and more customers, more and more successes in terms of actual implementation. And I think we're still on the early days of the company.
And now, when you're growing the company and bringing in new people, what kind of culture, what kind of team you're building at Neural Concept, and what does it mean in terms of how do you look at hiring people? What kind of qualities you look for, and what kind of people wouldn't be a good fit for the company?
So of course, there is the technical side, which is for us really key, and we have some quite strict interview procedures on the technical side, but that's just one part of the equation. We are trying to keep a culture. I mean, you can see the values of our company on our website, but really, we are really trying to build a company with people that are really down to earth, really pragmatic, honest, transparent. Also very demanding with what they achieve and what they deliver. Really, pushing this culture of let's say a mix between excellence on the one side and staying humble and down to earth on the other side. We also have, I mean, obviously based in Lausanne, which is the core of the company, so a lot of influence coming from, say, mountain sports, adventure sports, extreme sports. That are not everyone in the team is into that, but lots of people are, and even the ones who are not, I think, can adhere to the values that are also behind this type of sport.
You're all located in one office now, or you're open to hiring remotely as well?
No, so the most of the team is based in Lausanne, but we have an office in Munich, so hiring also out of Munich. Soon expanding to the US as well, with a not defined location yet. But I mean, anyone is welcome to apply. We also have a few people that were working in different places, trying to concentrate the activity in the core of the company in Lausanne, but we can be flexible.
And you mentioned that briefly, but let's kind of talk a little bit more about it. So you have an interesting relationship with world record setting. There is a human-powered vehicle that set 2 records that has been designed with using NC shape. And now you mentioned you're working on the boat that also is designed or supposed to be designed to break the world sailing speed record in 2024. So how did that work come about?
Yeah, this concept of trying to break world record and in different disciplines is, let's say, intimately linked and like really essentially linked to the idea of the core idea of optimization and numerical optimization, which is of course like also trying to break records in itself within the computer, and then hopefully hoping that it will translate into records in the real world. And so it came from different. I mean, it started through different meetings, different let's say different people that we met. I can take the example of the first the world record with the bicycle. It's quite nice. So we were really starting on the first version of NCS. And there is this team manager, Guillaume, who came to me and said, okay, can you we were introduced through some professor from EPFL and said, okay, can you try to do something there? And he wasn't sure. Okay, we're not really believing that we could do something. And then we started really launching the algorithm on an optimization and using some simulation and so on. And it was the first version of the software, so it took us a while to set it up. We launched an optimization, and the shape that came out was visually very close to the bike that had just broken the world record a few months earlier. Visually, and that's really what triggered the interest and really started exciting these people from this team, because they were thinking, okay, there were years of people designing and trying these bicycles of all shapes on the track, and this algorithm could maybe in 1 month, and we had no idea, we had never looked at this type of bicycle before, could come up with a design that was very close to the world record holder. And that's what I think really triggered this passion. And then, of course, the sailing boat record is it's also a project out of Lausanne that we're very close to, and I think our software is the perfect tool to, let's say, solve their needs in terms of performance of their hyperventilating hydrofoil. You can look on the internet; it's called SP80. It's a really cool project.
It is a very cool project indeed. And the bike speed record, do you think it would be possible without NCS?
I cannot say it would not be possible because there is another bike that was as fast and that didn't use NCS, but probably I don't know if the aerodynamics is as good, because this bicycle was going to break the world record again this year, but there's some few things happened. But it's really the speed of development for this shell that was quite amazing.
The other team, the one that you guys beat with your bicycle, did they come to talk to you also about designing one for them?
No, so no other team came to us. No, not yet. But we have one team that is close to our heart. So
I think it will take them some time, and then they will come around. Okay, let's switch to the future now. What are the long-term goals for the company?
So as I was saying, really the company is trying to develop this central intelligence that can connect and help the company take the best design decisions and faster. So now we are around a bit more than 30 people in the company. I think developing this system will require more and more people to work on the topic. So we will obviously grow the team to achieve that, continue to develop. I also develop collaborations with customers, because at the end of the day, that they are the ones who know what they need and who can help us be better every day.
So you're hiring. How can people learn more about the open positions?
Yeah, so on our website there is a hiring page. We are hiring across multiple positions, and really people should feel free to apply if they think that they can bring something to the team.
Okay, I'll add this link to the show notes. And where people can find the company online, on social media, and how they can check out the product.
So our website, of course, is a core platform, neuralconcept.com. We are also on LinkedIn, where we publish some news about the company. And I think sometimes we're on the news as well.
And you also have a blog with a bunch of very interesting articles and research papers that you guys publish.
Yeah, which is linked to our website, yes.
Yeah, I'll put all those links into the show notes. Sounds good. Pierre, thank you for joining me today. It was great talking to you.
Thank you. Thank you very much, Artem.